Sometimes even when you've seen the mark scheme, it still seems tough. And that's what these support videos are about. The higher paper for the mock is a horrible question, and we're going to have a little look through it. So in this first bit, we're told the submarine is being propelled forwards. We're being told it's moving forwards, and we're being shown some forces that are involved. We're being shown the thrust, which is the forward force, and the resistance forces acting in the opposite direction. We're told they're represented in magnitude. That word magnitude means size, so how big they are, how many newtons there are, and by direction using the arrowheads. So I can see immediately there that this thrust force is a bigger force in size or magnitude than the resistance force because the arrow is longer. So we're being asked which of the following is correct, and you may be very happy and have marked A and that's the right answer, but most importantly this is a chance to also review ideas and improve. So let's have a think. Which of Newton's laws is this question actually about? It's about law 1. The idea there is one object that we're focusing on here, that is the submarine and only the submarine. That one object has an unbalanced force working on it. It has a larger thrust force than it has a resistance force. There is a resultant force in a forward direction. So Newton's first law tells us that if there is no resultant force, nothing will change. So here, if the submarine was stationary and all the forces were balanced, it would stay stationary. If the submarine were moving forwards and all the forces were balanced on it, it would continue to move forwards, but it would not be able to get any faster or slower. Nothing would change. It would carry on moving forwards in exactly the same direction forwards. Here, however, we were told that the submarine was being propelled. So along with that diagram showing us and reminding us there is a resultant force here, it cannot be a constant speed. It cannot have a constant velocity. Something has to be changing. And as the forward force is greater than the back force, then it has to be accelerating forwards rather than decelerating in a forward direction. And that's why A has to be the right answer. Okay? Now that's very important to make the point there that Newton's first law focuses on one object, just the submarine, not the water around the submarine, but it also has part 2. In part 2 we're told that the propeller on this submarine forces water away from the back of the submarine. That sentence is mentioning 2 objects to me. It's mentioning the propeller and the water. Now remember, Newton's first law is always about one object, and Newton's second law is about one object as well. But Newton's third law is about 2 objects, and the fact that this first sentence is telling me about those 2 objects means my heckles are raised in this is a Newton's third law question. So if the propeller forces water away from the back of the submarine, explain why this produces a thrust in the forward direction. So the propeller is forcing water away backwards, and that makes the submarine move forwards. Why? Because every action has an equal and opposite reaction. By that statement of Newton's third law, by that I mean every action force has an equal in size force acting in the opposite direction. So here, when the propeller pushes on the water, so you've got a push from the submarine onto the water pushes back onto the submarine. Now, when the propeller pushes on the water, it will move the water out the way backwards. When the water pushes on the submarine with an equal size, that was a terrible drawing because those arrows should be the same length, an equal size but opposite direction push, when the propeller is pushing on the water, it pushes the water backwards. But the water pushes on the submarine, on the propeller, and that force is an equal size in the opposite direction, so it pushes the submarine forwards. To get those two marks, you're going to have to identify those two forces. You're going to have to say, for one mark, that there is a push from the water and there is a push from the submarine. And then to get the second mark, you're going to need to link in Newton's third law. And those two forces, those pushing forces, will be equal in size or magnitude, but they will be acting in opposite directions. So we still haven't finished part A of question 4, because now we've got part 3. So part 1 asked us about Newton's first law. Part 2 of it asked us about Newton's third law. And what do you see before you even read the question carefully? Explain using Newton's second law. So that's why this question 4A has been split into part 1, 2 and 3, because it's a question that's asking us about Newton's laws, applying Newton's 3 laws of motion. So the submarine is going to come to a standstill. Its engines are going to be put into reverse. The propeller will then run in a reverse direction, producing a force that causes the submarine to decelerate. It's going to take many minutes to come to a rest. That's not going to be instant. Like when you put your foot on the brake in the car, you don't instantly stop. So explain using Newton's second law why it would take many minutes for the submarine to slow down. And this no doubt has thrown some of you, because you'll immediately go, Newton's second law is F equals ma, which is one version of Newton's second law. I don't dispute that at all. It is. But there is another way of stating Newton's second law that we do in topic 2 in forces, and we do it when we think about momentum, and that's why this question is on a higher paper and not on a foundation paper. So what is Newton's second law? It is F equals ma. Those things, force, resultant force, is the F in newtons, the inertial mass, the mass in kilograms, and the acceleration in meters per second squared. We have to think about what acceleration is to understand where this equation comes from that I'm going to use as Newton's second law. Acceleration is the rate of change of velocity. It's the change of velocity in time. The final velocity, take away the initial velocity, is your change of velocity, and you're working out how long it takes for that velocity to change. Okay? So if something is accelerating, you have a higher final velocity than an initial velocity. If something is decelerating, then the final velocity is lower than the initial velocity, which is why you end up with a minus meters per second squared answer, because it's a deceleration instead of an acceleration. So, moving objects. Moving objects have momentum. Stationary objects don't. And that's what this question is linking to. This fact that the submarine is going to come to a standstill. When it's at a standstill, it will have no momentum. When it was moving, it had momentum. Had it, and now it's not going to have it. But to get from there to there, something has to happen to that momentum. Okay? We have to conserve momentum. So, when we think about Newton's second law, we think about F equals ma immediately, I hope. However, if we think about the fact that acceleration is a change of velocity in time, we could say F equals m times v minus t over u. Okay, I've replaced the acceleration with the definition of acceleration as an equation. Now, momentum is another property, a property of moving objects that you can find by doing the mass times the velocity. Okay? So, if we think about Newton's second law that I've expanded here to include acceleration, we can expand it further, because what we've actually got is mv minus mu over t. But if momentum is mass times velocity, what we've got here is the final velocity, take away the the final momentum, take away the initial momentum, and that means that force is the change of momentum over time. So to change momentum, you need a resultant force to be acting for a length of time. Big forces, small times. That's why cars have crumple zones. They increase the time of a collision to decrease the force on the people in the car. But let's link it back to this question about the submarine. Here you have got a submarine with a large mass. That large mass has a lot of momentum. We need time for a force to act to change the momentum from what it is to zero, to make it stationary. For that momentum to be in the moving water instead of in the moving submarine, so that it's still conserved. But the submarine is a huge mass, lots of momentum, therefore it is going to take a long time for the momentum to go to zero with that resultant force acting. Newton's second law is F equals ma, but it is also the change of momentum divided by time. They are the same equation, and I hope that my ramble through this has helped you to see that. So for this question, you do need to think about and state Newton's second law, but really you need to state it in this form. And you don't have to remember that form because that is actually on the formula sheet. That's one of the equations that you're not expected to remember. You do have to learn and apply F equals ma, but this one is actually on your formula sheet. You just have to remember that this is Newton's second law in another form. You have to think about the fact that because the submarine is so large, then it is going to take time for that momentum to change from having a large momentum to being zero. So it's a lot of thought and a lot of work to get those 2 marks. But this is the last question on a higher paper. So they are trying to separate grades here. They're trying to separate the 8s from the 9s, the 7s from the 8s. It's worth 2 marks because not many students in the country are going to be able to answer this question and get 1 or 2 marks from it.